Not discussing, rather, because it is a lengthy discussion, dynamics of viscous flows. So, the question is that what is so special about dynamics of viscous flows and why should we study this? There is absolutely no question in mind why should we study dynamics of viscous flows, because most practical flows are viscous flows. But what is so special about the analysis? The special feature of the analysis of dynamics of viscous flows is that you also have to consider the viscous forces, and we have to learn a formal way of representing the viscous forces. So, we will do that, but we will start with our very general Reynolds transport theorem and see that how we can express or how we can establish a governing equation for dynamics of viscous flows starting with the Reynolds transport theorem. So, now we will start with the Reynolds transport theorem for momentum conservation. By momentum we normally mean linear momentum, but let us write it explicitly. Now, what we do here is something like this. So, we start with the Reynolds transport theorem. For a control volume which can have arbitrary motion, but we first write for a control volume which is having a stationary nature. So, in that case you will have this framework is pretty general, because even if the control volume is accelerating, we have seen that this force has to be just corrected. This force will be the force minus some mass into acceleration, where that acceleration takes into account the pseudo forces. Now, when we make this analysis, we are not very specific to these forces, but from now onwards we will specify what are the forces which are acting on the system. So, there are two types of forces in continuum mechanics which can act on the system. One is called as surface force, another is called as body force. So, I will explain what each are. So what is the surface force? A surface force by nature is a force which acts over the surface of a control volume, that is a control surface. Normally these forces are expressed as force per unit area. So we will see how we write the surface force. Next there is a body force. This by the name it tells that it acts over a volume of the body, and then it is expressible as a force per unit volume. So let T represent a vector. So what we do is we take a surface like this, or this is a control volume. From that we take a chunk of volume and then we consider a surface and consider the force per unit area on that surface. This we are calling as T. This is called as traction vector. This is force per unit area. So this traction vector will essentially depend on certain things. For example, if instead of the orientation of the area like this, had the orientation of the area same dA but been like this force per unit area would have been different. That means this traction vector also depends on the orientation of the area chosen, or the unit vector of the normal, outward normal of the area. So to stress upon that, we give a superscript eta, indicate that this is the traction vector over an elemental surface which has an outward normal in the direction of eta. So then the surface force becomes okay. So this is force per unit area, this multiplied by the elemental area, then integrated over the control surface. Then what is the, so this is essentially force on the control volume. So one is a surface force which is force on the surface of the control volume, another is the body force. Let B be the body force per unit volume. So this is body force per unit volume. Then our next job will be to express this traction vector in terms of some known parameters. Those known parameters are called stress tensor parameters. Not that they are explicitly known, but they can be formalized or they can be expressed as a function of the velocity gradients in the flow. So in terms of stress tensor components. So what is a stress tensor component? We will come in a moment. So let us say that we have a surface like this or a volume like this with 6 faces. This we call as x, y and z. With the corresponding names as follows, alternative names. This alternative name is motivated by a notation called as index notation, where we can simply give that index I equal to 1 will mean x axis, I equal to 2 means y axis and I equal to 3 means z axis. Let us try to figure out. So we are just understanding the notation from here, not the change from this phase to this phase. We are not doing any such calculation. So the notation wise, what we do is we first write this force per unit area on this in terms of the T notation. So the traction vector, say the normal component of the traction vector. What is the normal of this vector, normal of this surface? The normal of this surface is x1 direction. So we give 1, and what is the force direction? That is also 1. So we give another 1. So we can write this T, its components with 2 indices, one index to specify the direction of the area, another index to specify the direction of the force. So this can be written for any area, but if we consider some special areas where the area is either normal to x axis or to y axis or to z axis, then this can be written in an equivalent notation tau 1 1. What is this first? Direction normal, the second is the direction of force. Okay. So in general, if you write tau ij, the first index I is for the normal to the surface and the second index is for the direction of force. This tau is this stress tensor component, tau ij. Why it is called as a tensor? See, it is more general than a vector. A vector requires one index for its specification. If you have a force F, you just write Fi. I equal to 1 will mean x component, I equal to 2 will mean y component, I equal to 3 means z component. But here just one component is not good enough. So it requires two components, so it is somewhat more general than a vector. So it is called as a second order tensor because it requires 2 indices for its specification. A third order tensor will require 3 indices for its specification. So we will come across examples in physical world where a fourth order tensor is also very important, and we will discuss that later on. But tensor, order of the tensor is not formally just fixed by the number of indices, because the indices are used for Cartesian representation of tensors, not just any arbitrary representation. So there is a more general requirement which a second order tensor has to fulfill. What is that requirement? A second order tensor must map a vector onto a vector, and we will see how that is possible in this example or in this case. Now, so this is tau 1 1. So I will just draw it for 2 surfaces. So what is this? These are all per unit area. So tau, what is the normal of this surface? Still the normal is 1. And what is the direction of the force? That is x2. So tau 1 2. And similarly, this is tau 1 3. Let us show it in the other one. So what is this? So this is also tau 1 1. I mean, just notation wise, actually if you consider from this phase to this phase there is a change, Taylor series expansion has to be used. I am not getting into that, this is just a notation diagram, this is not a diagram to actually show the real forces. So notation wise this is also tau 1 1, but we show its sign convention in the negative 1 direction. Why? Because the normal to this surface is negative 1 direction, that is the sign convention. Similarly, and this will be tau 1 3. Okay. So we have learned 2 notations. One is a traction vector based notation, another is the stress tensor component based notation. The stress tensor component based notation is very convenient because it talks about fixed areas, that is areas either perpendicular to x or y or z, whereas the traction vector concept is based on an arbitrary area. So it would be very nice if the traction vector is expressible in terms of the stress tensor components, and we will try to see how that is possible. So let us say that we take a volume like this, where this is x1 axis, this is x2 axis, and this is x3 axis. So we have 4 faces. Can you say that why out of so many possible types of volumes this type of volume is chosen? The answer is not that straightforward, but if you think deeply you will recognize that this has 4 faces. What are those 4 faces? So you have OAB, OBC, OAC and ABC. These are the 4 faces. Out of these 4 faces, 3 faces are very special. The first 3 faces have normals either along x1 or along x2 or along x3, but this has an arbitrary normal. So if we can write a force balance on this, then it is possible to express the traction vector in terms of the stress tensor components in the limit as we shrink this volume to 0. That is the motivation of choosing this volume. So let us say that the OAB, so this direction normal is x1 negative x1, OBC's direction normal is negative x2, OAC's direction normal is negative x3 and ABC's direction normal is say eta, which is eta 1 I plus eta 2 j plus eta 3 k, where eta 1, eta 2, eta 3 are the direction cosines of the vector eta. So now we will identify the forces along x1 direction. So what will be the forces along x1 direction? So first on OAB, so tau, the first index is 1 because the outward normal is 1 and the second index is also 1, minus because, or minus we will write in the equation because we have already shown the direction. This multiplied by, let us say, let us make another column in this table where we call this as area. So this is ds1, ds2, ds3 and ds, area and normal. So minus tau 11 into ds1. Similarly here tau, what is the direction normal here? 2. So tau 2 1 ds2, here these are all parallel. So let me draw it properly. This is tau 3 1 ds3 and on ABC what is the force? T, right? You cannot express it in the tau notation. So let us say T with superscript eta and subscript 1 and ds. So resultant force along x1 is the mass times acceleration along 1. Oh yes, not only that, I have not also written the body force which I should write. So the body force is what? Let us say that h is the perpendicular distance from O to ABC. So the body force is rho times the volume is 1/3 into ds into h into B1 is the body force per unit volume along rho will not be there, right, just we consider this is per unit volume we have taken, not per unit mass. So volume into B1, okay. So then Fx1 is minus tau 11 ds1 minus tau 21, so this is ds2, sorry, ds2 minus tau 31 ds3 plus T21 ds, sorry, oh, where from these 2 has come? Inertia of writing it has come, okay, right, because there cannot be anything called as T21, right, this has only one index traction vector and one at the top, another at the bottom, not 2 simultaneously, okay. T1 ds plus 1/3 ds into H into B1 is equal to rho into 1/3 into ds into H into A1, mass into acceleration, okay. Now if you look into this picture or diagram very clearly, ds1, what is this? This is nothing but the projection of the ds area on x2 x3 plane, right, projection of this big triangle onto the x2 x3 plane. That means ds1 will be ds times the dot product of their respective unit vectors. So what is the, so the unit vector here is I, here is j, here is k. So the dot product of this and this will be eta 1. So ds1 will be ds into eta 1. So let us write this as ds into eta 1. Similarly this will be ds into eta 2 and this will be ds into eta 3, okay. So now you can cancel ds from both sides and take the limit as h tends to 0. If you take the limit as h tends to 0, this entire volume will shrink to the point O. Then what you get is minus tau 11 minus tau 21 minus tau 31 plus tau 11 eta 1 eta 2 eta 3 plus T1 eta is equal to 0, right, because if you take the limit as h tends to 0, body force does not matter and acceleration does not matter. So it is not really a problem of statics, it is a general dynamic problem, but the force balance is governed by the stress tensor. So T1 so now similarly you can write similar expressions for T2 and T3. So you can write it in a matrix form. So tau 11, tau 21, tau 3 1, right. Next will be so the normal has come in the second index. So here the normal, let us write the second index. So 1 2 3, the normal has come here in the second index, which is 3. Okay. So you can see here is that the components of the stress tensor apparently 9, and we will see that there are actually 6 independent and not 9 independent components, but at least this is mapping this vector onto the traction vector. So this is a direction vector of the arbitrary area, it is mapping this vector onto the traction vector, and that is why this is a second order tensor. It is mapping a vector onto a vector. Because it is mapping a vector onto a vector, it is expressible in terms of matrix operation, and that makes it very convenient to write it in terms of the components in a matrix. So we will stop here today and we will continue with this in the next lecture. Thank you.